like that order which is very plain, there's not much, which has been developed generated from some deterministic system.
Yeah. I think that's a $1 million question. You really need to have what I would call informative data, as I explained earlier. If there's not much information in the data, no variance at all, and if your data are not representative of how you run your system, then you're unlikely to build a model that's useful. Right? Now, I've said unlikely, representative of true system, et cetera. Those are all very vague. The question is, how do you quantify it, right? I would say there's probably no easy way to quantify that. There are ways in which you can measure informativeness of a data set. I'll give you a simple example. Let's say you're trying to build a least squares model. Say you're using autoregressive exogenous input models, ARX models, right? You can solve for the model parameters by solving a least squares problem. When you solve a least squares problem, there is a matrix that you have to invert, right? And that matrix typically will have the measured data, the inputs and the outputs. Now, if you can't invert that matrix, then you won't be able to find reliable estimates of your parameters, right? So what it means is if your inputs and outputs are, let's say, as an extreme case, they're constant, they're not changing at all, then you will not be able to invert that matrix, and therefore you will not get a reliable model, right? Then how do we get a reliable model? We have to make sure that the inputs are changing. They are perhaps random, right? And then you will be able to have a good condition number for that matrix that you have to invert. When that happens, then you'll get a really good, reliable model. Right? If you don't have good data, informative data, what happens is when you go through these modeling exercises, you'll get a model, but you'll also have significant uncertainty around the parameters of the model. So when you have significant uncertainty, it's not very useful. Right? There is an entire area of research on design of experiments. Right? So how do you generate your data? You generate your data in such a way that when you apply your modeling algorithm to that data, the variance or the MSE, mean squared error, on the model parameters is minimized. There are formal ways of designing your data sets using optimization tools. You minimize the variance. So I can perhaps write this. So let's take a very simple example. You see, you have some y equal to some alpha times x plus some noise, right? Now you want to estimate alpha. X's are your inputs. Y's are your outputs. So you can solve this using least squares. You get an estimate of alpha, where you find the pseudo-inverse of some matrix times y. Right? Now, if this matrix has to be invertible, then you have to choose some. You have to choose your inputs appropriately, right? So this matrix is going to have x and y in it. Okay. So you have to choose your inputs in such a way that this matrix is invertible. Typically, what we do in experiment design is we formulate a problem of the following type. You minimize the covariance of alpha hat. In this case, I have a univariate least squares problem, but you can have a vector here instead of a scalar. So you minimize the covariance of this with respect to your inputs, which are x. Right. Sorry, I'm doing a little bit of hand waving here, not using proper notation, but that's roughly what you want to do. You want to choose your x's in such a way that the covariance of estimated parameters is minimized. Okay. Now, if alpha hat is not a scalar, then covariance is a matrix. Minimizing a matrix does not make sense. You have to find some scalar function of the matrix. There are different types of scalar functions of covariance matrix. For instance, you can minimize the trace of the covariance matrix. This is called T optimal experiment design. You can minimize the eigenvalue of the covariance matrix. So that's, I think that's called E-optimal design. You can minimize determinant of this covariance matrix. That's called D-optimal. There are many other ways in which you can design your X's or inputs. That's how you generate the right data for to make sure your parameter estimates are reliable. Now this is the formal way of doing it, and I don't normally use this approach. It's just a bit cumbersome. The rule of thumb is that you design your experiments, you design or generate your data in such a way that there's enough information, there's enough variance in the data, right? If you don't have enough variance, then this matrix here will not be invertible, and therefore you'll not get reliable estimates of your parameters. And sorry, I'm a little jet lagged. So your second question is about first principles models and do we really need to use data to upgrade or update the first principles models, right?
So my another question was that if we are generating data using some deterministic system, some process,
Right.
for example of mine, so I'm generating some data, and to use, let us say, to reduce the complexity of that problem, I come up with some machine learning module or machine learning program. So is it worthwhile because I already have a deterministic system which is giving a good data? So just to, one thing could be is I reduce the complexity of the problem. That could be one application. But
Right.
other than that, there is any other scope which is worthwhile to do such thing.
Right, yeah. So let me, I think the answer to that question depends on the type of system you have. There are certain types of systems, especially mechanical systems or maybe even electrical systems, that are very precisely defined by the physics or the mechanics of that particular system, right? And we often tend to have really good models with very good measurements. Then you are probably better off using those mechanistic or phenomenological models, if you can use them. Okay. On the other hand, if your systems are complex, this is mostly true in the process industries, we don't really understand the underlying physics or the chemistry or the biology, and this is true in biological systems as well. We don't have a good understanding of what's under the hood, but we have some measurements, right? Then what happens is, over the years, you might find in certain areas approximations of the underlying dynamics using first principles. Okay, but those first principles models are often inadequate to describe the behavior of your system precisely. So now you have this discrepancy between what you see from your experiments and in the data and what your science is going to model. Right? There's going to be this discrepancy. And if that discrepancy is large enough that you can't really use the models, the scientific models that you have, then it's a good idea to generate additional data, use that data in conjunction with the scientific model to build an upgraded model that's much better at simulating your system or predicting the future outputs of your system, right? So those models are called hybrid models. I've not included it in my presentations, but I think somebody else is going to talk about hybrid models. I think that's the way to go with engineering systems. You don't want to rely solely on mechanistic or phenomenological models. Instead, you also want to use any additional data information you have in upgrading your models. So those are called hybrid models. Sorry, did you say servant model? Surrogate models, yeah. Surrogate models, yeah, they're different names, hybrid models, surrogate. Surrogate models are basically a representation of your true system that in a way behaves like your true system, right? So that's a surrogate model. It's not the real model, but it's a surrogate model that replicates the behavior of your true system. You may have heard of digital twins. I mean, there are subtle differences between how these things are defined. In the literature, digital twins is a very hot area right now. And the goal there is to build a true replica of whatever system you have, not just a simple unit or a single system, but perhaps a complex interconnected set of systems, let's say, right? So that you want to replicate that behavior in its entirety in software. That is a digital twin. Now we have, I currently have a project where we are trying to build a digital twin for lithium-ion battery manufacturing. So if you take lithium-ion battery manufacturing, there are many different stages that you have to go through. So you have to take the battery material, we create a slurry, you mix it, and then you spread it on a sheet to make the electrode. Then you have to make sure that the properties of the electrode are uniform across the system. And then once that's done, once the electrode is prepared, you cut it and then you roll them into batteries or cells, and then you test them and send them out, right? So that's roughly the entire lithium battery manufacturing process. Now we want to build a digital twin of that for simulations, for analysis, for optimization, for tuning controllers, and so on and so forth, right? So digital twins are also very popular. Surrogate models, hybrid models. You've probably also heard of scientific machine learning or physics-inspired neural networks. I don't know if you've heard of those. But those are all different versions or different variations of surrogate models, yeah. New terms are coming into market, yeah. All right, sounds good. Okay, so can we get started? Are there any other questions? No? Okay. Yeah.
As I am doing my degree in IoT, so IoT uses different number of different types of sensors to collect data.
Yeah.
So there is physical data and there is analog data. So the data is independent of the source, or what is data? Is it only numbers? Or it can be anything?
Oh, I see. Okay. Yeah. As we're going to go through this presentation, I'll talk about different types of data. Now, the really cool thing about modern machine learning tools is that your data doesn't have to be just time series data. So you can have time series data, you can have images, you can have text, you can have videos, you can have categorical data, all sorts of data, which I call heterogeneous data, can be mixed and used in building models. Right? So it doesn't have to be just time series data. In fact, the most popular machine learning model is probably ChatGPT, right? All these large language models, they all use text data. In the process industries, in engineering especially, for many decades, we've primarily used time series data. We've also used some categorical data, perhaps. But it wasn't very common prior to these large language models for engineers to use text data. Right? There have been many applications of video data, maybe images, but not text data. Right? I think with the tools that we have, the powerful tools that we have today, we can use a wide range of data sets in building models, which I think is going to improve the performance of your models. The more information you provide these models, in some ways, could be better in terms of how these models perform. Right? It's not always true, but I would say in many cases, if you provide more data, different forms of data, it's good for the model building exercise. Does that answer your question? Okay. All right, are there any other questions? Okay, so if not, what I'm going to do is take you through my slides. I wanted to, in the first lecture, I wanted to tell you a little bit about why there is so much interest in artificial intelligence today. When I went to school, when I was doing my PhD, I had friends in computer science who were doing PhDs in artificial intelligence at that time. This was early 2000s, and they would always complain that there was no future for artificial intelligence, right? And this was in early 2000s. We're in a completely different landscape right now. And I wanted to take you through the history, as I saw it, of how this interest in artificial intelligence has peaked over the last 10 years or so. And I'm particularly proud of that because UBC, University of Toronto, and other Canadian institutions have had a major role to play in the resurgence of artificial intelligence. All right, before I get into that presentation, I just wanted to show you the schedule for the next 5 days or so. You've seen this, did you all receive this? So I'm going to be doing lecturing for about 2.5 hours or so a day, and then we have a couple of other guest lectures as well. We are also going to be doing several demonstrations, I think, of software in the afternoon. I also have Python notebooks. How many of you here use Python for machine learning? Okay, so not a lot, but if you've not used Python, not to worry. Python is a very easy language to learn. If you've used, I'm guessing if you're not using Python, you're using MATLAB. You know, I was trained in using MATLAB when I was doing my PhD, and even later as an assistant professor, I was primarily using MATLAB. But since about 2015 or so, I've asked all my students to shift to Python, partly because at that time, when there was this renewed interest in artificial intelligence with the development of tools or algorithms such as deep learning, there was, you know, a lot of those tools were available in Python, not necessarily immediately in MATLAB. So some of my students who were doing some cutting-edge research in those areas, they shifted to Python. Since then, a lot of my other students also shifted to Python. But I really like MATLAB because you know, that's the language that I grew up with. It has some really amazing toolboxes, especially if you're doing signal processing or control systems. I believe they've also developed various toolboxes for modern artificial intelligence algorithms as well, although I've not used them. I've primarily used Python. I don't, unfortunately, have codes in MATLAB, but I have created, with the help of some of my students, several Python notebooks for performing various machine learning tasks, starting from data processing, data pre-processing, to trying out different algorithms. I also have sample data sets. So what you can do is take these Python notebooks, take the sample data sets, load the data, run through the code, and understand how different machine learning algorithms are implemented. Okay? So I'll share those files and folders with you at your leisure. You can try those. I generally use Google Colab for running my Python code. If you don't have a Google account, please get a Google account. Colab.google.com is the website where you can load Python notebooks and run them. All right? Now, you've seen the topics that we've listed here. There are many other topics that we can cover. I wanted to ask you if these topics are appealing to you, or if there is something missing, something that you would like us to cover. If so, then I can come back to you in a couple of days towards the end of this course. I can come back to you and perhaps talk about those topics as well. All right? You don't have to answer this question right now. Go back after this presentation later this evening, think about it, and come back tomorrow and let me know if there are topics that you would like me to cover that are not listed here. Okay. All right. This is a talk that I prepared for the general public. It's not very technical, but I think that's where we should start, just to get an idea of where we are heading with artificial intelligence. Where did we start? Where are we heading? What has really changed in the last few years? Why is it that there is so much interest in artificial intelligence right now? Now, this work, I'm going to show you some results from my own research work. There are many, many students that have contributed to that research work. Obviously, I need to thank them all. The list is really long. Some of my students are listed over there. And when I talk about specific applications of artificial intelligence, I will also identify the students who have worked on those projects. So there is this enormous hype around artificial intelligence, right? You've heard about it. You probably constantly hear about it in the media, in advertisements. Everybody is promoting their products, saying there is some AI element to it, et cetera, et cetera. Some of that is perhaps hype. There are really big companies with almost unlimited supply of funding that are behind the resurgence of artificial intelligence, and therefore you are likely to hear about it in the media, in ads, and so on and so forth, right? I think some of it is really hype, right? But at the same time, I remain very optimistic that we can use these tools to really change the level of automation in engineering systems, right? There are some areas of engineering where there's an enormous amount of automation that's already there. But I think with the new tools that we have access to, we can improve the level of automation and make everybody, the engineers especially, very, very productive with what they do. Okay. And to do that, we have to figure out new ways of using the data that we already have. Okay. All right. Has anyone heard of Yuval Harari? No? Okay. So he's a well-known author from, I believe he's from Israel. He had written a book. His first book, or first book that I am aware of, is *Sapiens*. It talks about the history of human civilization over the last 2,000 years. And it's a really fascinating book because he talks about how, as humans, we have come to dominate the planet. There are just so many other species on the planet. Why is it that we as humans are able to dominate the planet, right? So he talks about that. It's a very, very nice book. If you get a chance, do read it. And his second book, the book that followed *Sapiens*, was *Homo Deus*. And this book talks about the future, the next 300 years. And he says in the book, in the 20th century, the main products will not be textiles, vehicles, but bodies, brains, and minds. AI and biotechnology will give us godlike abilities to re-engineer life and create new life forms. Right? So he's sounding very optimistic there. And in fact, he says in about 300 years from now, every newborn baby is going to be implanted with a chip, and then they know everything in the world with the chip, right? I don't know if we're going to get there or not, but that's the prediction. But is it possible? Perhaps, right? But the pace at which innovation in AI and related areas is moving, I think it's not too far-fetched an idea. So I told you that I was going to talk about the resurgence of artificial intelligence, right? Artificial intelligence as a term was, I believe, coined sometime in 1950s. People were building very simple tools that would automatically accomplish certain tasks. So that's when artificial intelligence as a term was coined. But I'm not going to focus on that. I want to focus on what happened in the last 15 to 20 years, and why is it that there is so much interest in artificial intelligence right now. Okay, so what has changed? As I mentioned earlier, I had friends doing PhDs in early 2000s in artificial intelligence who were really not, they were not expecting that artificial intelligence is going to change the lives of everybody, right? So they thought it was a dead area, not an area that anybody should be working in. But that has really changed in the last 20 years or so. And why is that the case? Internet of Things, I know there are some of you here who are doing bachelor's in Internet of Things. The number of devices, instruments that are connected to the internet has really exploded over the last 20 years. And the graph here on the right-hand side shows that trajectory. And I think this, the number of devices we are installing is continuing to increase at an unprecedented pace. Okay, so what it means is we are generating enormous volumes of data that did not exist just a few years ago. The picture that you see on the left-hand side is from the cover page of Economist, where they were talking about the data deluge. Right? There's enormous volumes of data, and that's what is called big data. Right? So big data is defined formally. I will get to that in a bit, but we have this enormous volume of data, and the rate of generation of this data is continuing to explode. Right? If you take 20 years ago, we didn't have that much data. We had some data. There's some data on the internet, but we all did not have our personal devices, right? And that has changed in the last 15 to 20 years. I'm almost certain that everybody in this room has a cell phone or maybe a laptop. You probably are generating lots of data every day through images, text, et cetera, et cetera. There is enormous volumes of data that we are all generating every day. In addition to that, there have also been major improvements in computing power, right? So for many years, the processing chips followed the Moore's law, and their computing power kept getting better and better and better, right? Now we are probably, quantum computing is probably not too far away. There are people who are optimistic that quantum computing is going to be another leap in terms of the computing power that we will have access to. NVIDIA has been releasing new GPUs very frequently. Their latest GPU is called Blackwell B200 that is meant for artificial intelligence applications. These companies are building artificial intelligence specific chips that are much faster, more efficient for artificial intelligence algorithms. And finally, we've also seen major algorithmic advances in the last few years, right? Especially the invention of deep learning algorithms that has really changed the pace at which we are able to solve a wide range of long-standing scientific problems. So I think it's this serendipitous confluence of Internet of Things, the data we are generating, the computing power we have access to, and the algorithmic advances that have really resulted in the revival of interest in artificial intelligence. When it comes to computing power, you're all probably, I'm guessing you're all around 20 years old. You're probably born in this century. But in the 1980s, computers used to be as large as a room, perhaps this room, right? They're not, and they were not all that powerful compared to what we have today. But the watch that I'm wearing is probably more powerful than the computers we had in the 1980s. So, and the pace of computing power is also accelerating. You've probably heard of how much energy it takes to build large language models, the amount of computing power that these models require. Right? So in the last 20 years, we've had this serendipitous confluence of IoT, data, computing power, algorithmic advances, and therefore more interest in artificial intelligence. So how did we go from early 2000s where people were not sure that artificial intelligence is something that we should be pursuing, to where we are now, where a number of leading AI researchers are predicting that we will have superintelligence or artificial general intelligence in the next few years. Right? How did we go from 2000, where nobody wanted to do a PhD in artificial intelligence, to where we are now, where there is so much optimism around what is possible through artificial intelligence? And I think it has to do with two stories, two sort of independent stories that merged in 2008 or 9 to get us to where we are today. And I'm going to narrate those two stories. And as I mentioned earlier, both of those stories have some connection to Canada. So let me start with Eric Lindholm. Eric Lindholm is a chief scientist at NVIDIA. You've all heard of NVIDIA, right? NVIDIA is a chip manufacturing company. It was started by Jensen Huang in the 1990s. And when the company was started in the 1990s, Eric Lindholm, I think, joined them sometime in 1997 or so. And they were trying to build chips that are useful in gaming. Right? So gaming, if you've played games, there are a lot of graphics, you have to load them. It consumes significant computing power. And in those days, Intel was the top manufacturer of chips for personal computers or for servers and so on. They were making CPUs, central processing units, and CPUs generally execute commands sequentially, not parallelly, right? So it executes one command, and then the next command, and then the next command. The idea behind GPUs or graphics processing units is that if you can execute multiple commands simultaneously in parallel, then you can make these chips much, much faster. Right? So the very first GPU, general processing unit, was built by Eric Lindholm, designed by Eric Lindholm. He worked with some of his colleagues at NVIDIA, and they released that first GPU in early 2000s. Okay. And Eric Lindholm graduated from University of British Columbia in I believe, late 1980s. The photo that you see is of Eric Lindholm with our president and chancellor. They just honored him with a doctorate just a couple of months ago. Okay. So, and Eric Lindholm was the first person to design this GPU. And then what happened was around 2008 or 2009, they realized that these GPUs have much broader applications than just in gaming. You can do certain types of complex matrix multiplications using GPUs. You can do those multiplications much, much faster than on CPUs. That's something that they realized. And the problem was, in order to have everybody, the researchers, access to the GPUs, they needed a new language, new coding language, which is called CUDA. So they developed CUDA and opened up these GPUs for other researchers who might want to use the power of parallel processing of commands. Right? So they developed this language called CUDA, and they put these GPUs out. That's when Geoffrey Hinton's team jumped on that opportunity and designed new algorithms for machine learning. So let me take a pause here on this thread, and let me tell you what was happening on Geoffrey Hinton's team. Geoffrey Hinton is a British scientist. He was at Carnegie Mellon University for a bit, and then he moved to University of Toronto, perhaps sometime in 1980s. And he and his colleagues, they were working on building better neural networks. Right? We'll talk about neural networks in a bit, but they were trying to build these networks that perform better. Okay, but one of the problems they faced was if they had more than a few layers in the neural network, then it's extremely difficult to train those neural networks because of the computational intensity, computational complexity. It is difficult to train neural networks with multiple layers. And his students, Ilya Sutskever and Alex Krzyzewski, they figured out that they can use these GPUs to train neural networks because there are some computations in training neural networks that can be executed in a parallel fashion, not necessarily sequentially. So they used CUDA from NVIDIA and their GPUs to train larger neural networks. And that was a major breakthrough. They published their paper in 2012, and those neural networks are called deep neural networks. It's also called deep learning. And they're all from University of Toronto, which is also in Canada. And so that's why I was telling you that Canada played a really important, major role in the revival of interest in artificial intelligence. You might know Geoffrey Hinton received a Nobel Prize in physics last year in 2024. And he's not really a physicist, but I found it fascinating that they would give a Nobel Prize in physics to somebody from computer science. The Nobel Prize in chemistry also went to, I would say, a non-chemist last year. It went to Demis Hassabis, who started a company called DeepMind in UK. And their invention was a software called AlphaFold that predicts the folding of proteins, which is useful in drug discoveries. They use deep learning and related ideas, reinforcement learning, and so on. So that's really how we ended up where we are today. The development of these chips, and then the development of the deep learning algorithms. Please pause me if you have any questions or you want to comment or add something to Surendra. Please, if you want to add something to what I'm saying, feel free to do so. Now, I talked about the students of Geoffrey Hinton developing deep learning, right? Or deep neural networks. So how did that happen? For many years, there used to be the ImageNet classification challenge. Has anyone heard of this? ImageNet classification challenge. I think it started sometime in early 2000s. The challenge involves classifying approximately 14 million images. There are about 1,000 classes of images. These are everyday objects. I think only a small subset of those images were actually labeled. Maybe people have labeled more images right now, but when this competition used to happen, about 1.4 or 5 million images were labeled. And the competition involves developing an algorithm that takes these images, okay, and classifies them correctly. You have 1,000 different classes, right? So you feed these images to your algorithm and check if it's able to detect the objects in those images accurately. Now, this competition went on for many years, and in 2010, for instance, the best-in-class algorithms produced an error of about 28%. That's a huge error, right? So meaning the best-in-class algorithms, they would only identify the correct object approximately once every 3 times or once every 4 times, right? That's the best that those algorithms were able to do. And the algorithms were getting better and better, but only very slightly. Year after year, they were getting better, but only very slightly. And you'll see in 2012, something dramatic happened. You went from about 26% in errors to about 16 or 17% in errors. So roughly a 10% shift in errors of this ImageNet classification problem. And that was because of the work that Geoffrey Hinton and his students did using deep neural networks, by adding more layers to the neural network, using GPUs to train those neural networks. And certainly when the deep neural networks came out, people started finding other variants of deep neural networks and applying those variants on the same problem. And in over a few years, the errors with the best-in-class algorithms on this problem came down to something like 2.5% or so. I think these errors are even lower right now. And that error rate is, in fact, better than, apparently, the human error rate. If you have to label 1 million images that are probably grainy, not very clear, etc., humans are likely to make errors as well. And these tools that we have today for image classification that are using deep learning are much better than humans. Okay. Since that invention, deep neural networks, a lot of other breakthroughs have occurred. There was a special edition of the Time magazine in 2018 where they talked about all the breakthroughs in computer science in the last few years, and they come to the conclusion that there is a central breakthrough behind all of these other breakthroughs, and that central breakthrough is the development of deep neural networks or deep learning. On the left-hand side, you see image classification. There's a video. The algorithm there, convolutional neural networks, they're able to identify different objects in the video. And that, I believe, happened sometime around 2012, 2013. We'd also seen breakthroughs in speech recognition. The latest algorithms for speech recognition are just so good that they can listen to even a child and interpret or translate what they are saying. So we've seen breakthroughs in speech recognition, self-driving cars. I'm going to show you my own experience in a self-driving car. I think they started putting them on the road sometime around 2014, 2013. Now, if you go to San Francisco and a few other cities in the US, they actually have these self-driving cars running on the streets. Natural language understanding, there were significant improvements there in 2015, 2016, and so on. But in 2022, we had seen these large language models that have a really good understanding of natural language. They can interact with you just as humans would. Okay? Human level control in games. Alpha, has anyone heard of AlphaGo? Yeah, so it's one person. There are now AI-based bots that play chess, for instance. These bots are so good that some grandmasters were saying that these bots are finding new variants of chess matches that they had never thought of before, right? And I believe a number of grandmasters are now using these AI bots to train for chess matches. AlphaGo is a software that plays the game of Go. I don't think we play Go in India. Is that played in India? Do you know what Go is? It's played in a lot of other Asian countries, in China and Korea, maybe Japan as well. It's not like chess, but it's a little different. There are a number of squares, just like a chessboard. I don't know how many squares on it, and there are small coins that you move around. I never played it myself, but it's supposed to be a lot more complex than chess because of the number of variations you can have in that game. So AlphaGo was a software that was developed by DeepMind in 2017 or 18, around there. The world champion of Go used to be at that time from South Korea. He played with AlphaGo. I think he won one game but lost 4. At the end of it, he just simply could not believe that a piece of software could defeat him. Right? We can also do machine translation. Some of you probably have apps on your smartphones that can convert any language into any other language. You can do that on the fly. Complex Go game, I mentioned that already. You can do text-to-speech. That's something that we are using in our everyday activities. Text-to-image, we can also take an image and ask these tools to interpret or tell us what is in in those images. Right? Okay, so this chart here shows the development of different applications in artificial intelligence in the last 10 years or so. And as you will notice, all of this started in 2012, and 2012 is also the year when Jeffrey Hinton and his students published a paper on deep learning. Right? So deep learning was really an inflection point in the innovations that happened in artificial intelligence. It led to all of these other things. ChatGPT was released in November 2022 for the public, right? And I think ChatGPT, the release of ChatGPT is also an inflection point in different ways. It's an inflection point for universities, higher educational institutions. We need to really figure out how to train students in this era where they have access to this very powerful tool that can solve their assignments or answer any questions they have. Right? So we're struggling to figure out how education needs to evolve in the context of some of these tools. All right. Now I want to give you some examples. I hope I can play these videos of how AI is really changing the lives of people. So first one is from Neuralink. Oops. I think, okay, so I have to connect to, is there a Wi-Fi I can connect? LH1? This one, okay. It's open, so no password is required. Okay, all right, yeah. Have you heard of Neuralink? Yeah. No? Okay. Neuralink is a company owned by Elon Musk. They're developing chips that can be implanted in certain types of patients who have trouble with, with moving their body parts. Patients who are suffering from paralysis and so on. So they implant these chips in the brain and let them have a better quality of life. Let's see if it, okay, yeah. Oops, sorry, let me play this again. I should probably play it on YouTube so you can see it better. Sorry, I'll play it on. I'll see if I can play it on YouTube. Okay, that's not working, so we'll have to unfortunately start here. I'll stay quiet. Yeah. It's here. The paste. pasted this one. This is a product that was developed at MIT, I believe. I want to impress upon you that AI is really changing all our lives, or is going to change our lives.
What is 45,689 divided by 67?
Sure.
He silently asks the computer and then hears the answer through vibrations transmitted through his skull and into his inner ear.
6, 8, 1.9, 2, 5.
Exactly right. One more. What's the largest city in Bulgaria, and what is the population? The screen shows how long it takes the computer to read the words that he's saying to himself.
Sofia, 1.21 million.
That is correct. You just Googled that.
I did.
You could be an expert in any subject. You have the entire internet in your head.
That's the idea.
I have a couple of other examples. This is something that's really fun to watch.
When Demis Hassabis won the Nobel Prize last year,
Okay, let's close that. Check out these robots that are being built at Stanford in the research group of Chelsea Finn. All right. You'll find on their website, you'll find a lot of really fun videos to watch. When you go home, try watching those videos. Okay. Where's my slide deck? Okay. Sorry? Yeah, you can give it. So they use something called, I believe, imitation learning. So the way it works is, so what you will see later on as we go through the AI tools. One challenge with the AI tools is that they often require significant amount of data, right? So for instance, I'm going to talk about reinforcement learning in a couple of days. Those tools require enormous amount of data to train because reinforcement learning in its off-the-shelf version does not need, in theory, a model to train. It'll just interact with the system, generate a lot of data, and then it'll learn, right? But as you can imagine, that requires significant amount of data, right? What time are we stopping? 1 o'clock. 1 o'clock. Okay. So we'll stop, pause at 1, and then we'll come back. When we come back, I'll continue in the afternoon. But if you think about it, as if you have observed a child, right? If you teach them how to pick a pencil, you show them once or twice, and then the third time, they know how to pick it, right? And then you don't have to teach them how to pick a marker, right? You just teach them how to pick a pencil, and then they can pick a marker. But the machine learning algorithms don't seem to carry the knowledge or the meta skills of what they have seen before, right? You're often starting from scratch again and again and rebuilding your algorithm. So what it means is you need lots of data, right? So over the last few years, there was this idea that we should figure out how to train things much faster with limited amount of data. That's how humans learn, right? And can we carry our learning, the way we learn, to these algorithms? So there's a lot of work that the people at Stanford and Berkeley have done in that area, where their goal is to minimize the number of interactions you're going to have with the environment when you train these systems. So another example that I often give is, we have 2 young kids. Our daughter is now 8 years old, but when she was 4, we put her on a balance. Sorry, not when she was 4. Maybe when she was 2, we gave her a balance bike. Did anyone here ride a balance bike when you were a kid? Do you know what a balance bike is? No? A balance bike is essentially a bike, but with no pedals, right? It just has wheels. Kids sit on the balance bike, and then I have a video of my daughter doing that. If I can find it, I'll show it to you in the afternoon. So kids sit on these balance bikes. They push with their legs. They just balance. There's no pedal, and it's a really easy bike to ride. When kids are 2 years old, they just master it in a few days, right? But I remember learning to ride a bike and falling and injuring myself several times, right? It was not easy when I learned how to ride a bike. So our daughter, she was on this balance bike for maybe a year or so. And then when we moved her to a pedal bike, I actually have a video of this. In 2 minutes, she was able to master a pedal bike, right? Because she already learned how to balance the bike. And when we transferred her to a pedal bike, she didn't know how to get started, but when she got started, it was very easy to use a pedal bike because she already knew how to balance, right? So with every task that you learn, there are certain meta skills that you're also learning. So in the case of the bike, balancing is a meta skill that she learned. And it was just so easy to transfer to a new task, which involved riding a pedal bike, right? So the idea there is when you learn something, there are these meta skills that you can carry to other tasks. There's something called meta reinforcement learning that originated from similar ideas. With these robots, I believe they use what is called imitation learning. If you go to their website, you will find some of their training videos as well. So you see 2 arms with that robot. In the training videos, you actually have a PhD student with their hands in the arms and doing the same tasks. And if you use the traditional classical machine learning tools, you would probably need a student cook that omelet 1 million times before your robot learns how to do that. But that's not practical, right? In many applications, you cannot have somebody do a certain task 1 million times or 2 million times. So with the tools that they're developing, I think towards the end of the video, they say they trained it on 2 chairs, and then it was able to adjust the other chairs automatically, right? So there's some special interesting tools that they're using there to minimize the amount of data required to train these algorithms. All right. Any questions there? Yes, please.
Hello, sir.
Yeah.
So there are 2 questions. First question, sir. So don't you think, as you told that, these AI bots and all those technologies needs to be trained. So is storage is not a problem with these technologies, because somehow you have to feed in data and that has to be stored somewhere, and they keep on learning. So they are also storing somewhere in it. That is
Right.
first question. So is it not a hurdle? Second thing, how these algorithms cope up when altogether different environment is put to them. For instance, let's talk about Tesla. If Tesla comes to India, we have cows and dogs in our streets. So does those technologies are equipped to handle such cases, or it will take some time to learn?
Right, yeah. Great question. So in terms of data, so you're typically storing the models. Yeah, you train the models have some parameters, you keep the model. Do you need, once you have the model, you don't generally need the data, but if there is, we have massive data storage facilities right now. And all of you here probably have an account on Dropbox and all of these, the other tools. Data storage, I've not heard that being a problem, right? So I think, yeah, I don't think data storage is a problem. What's your second question? Sorry. Yeah.
How these algorithms cope up with the altogether different environment.
I see. Yeah.
Tesla was the example I gave to you.
Yeah. I think they released robo-taxis yesterday, Tesla. I'll show you a video of a self-driving car. This is a Waymo car. Waymo is a subsidiary of Google, or Alphabet, I guess. It's owned by Alphabet. They've been in this area for maybe 10 years or so. They now have cars that are running in San Francisco, maybe LA, Phoenix, Austin, and a few other cities. But what I know is they train these cars over many, many years. So they just went through the same streets in San Francisco every day, right? Maybe for many hours. And they trained them over many years. So if they find a new environment, how do they respond? How do they react, right? So, I mean, they can still make mistakes, but it's very rare that they make mistakes. And I'll give you an example of my own experience in just a bit. But, the idea of these models, these cars, is that, you build your models, you put your safety constraints on them, and hope that they will react in the best possible manner in every situation you put them in, right? So there's some very robust algorithms behind these technologies that allow you to do that. They may even have many safety features, right? If it doesn't understand the environment it's in, it probably shouldn't take any risky actions, right? So just stay there. So I've driven in self-driving cars several times, and once we were going on a 2-lane road. It's a 2-lane road basically. You have 2 lanes. There's traffic going this direction. There's traffic going in this direction, right? So and on this lane, there was a bus occupying almost the entire lane, and our car was over here. The bus had flashing lights on it. So there's traffic in the opposite direction over here. So Waymo, it stopped right behind the bus and stayed there for a few seconds, maybe 30 seconds or so. We got a bit worried because when it's riding, you can't even go out, right? All the doors are locked. You can call their support service when you're in the car. So we called them, and just when we were telling them our situation, the car figured out that this bus is not going to move because it had its flashing lights on, and it slowly moved into the other lane and then came back. I mean, I don't know how a lot of these technologies are proprietary, so we don't know fully what they're using. But I would expect that these systems are designed in such a way that they can cope up with unseen environments and situations. There's a company called Wave. It's out of London, I believe. Last year they were planning to move to Vancouver from London. And as you might know, in London, you drive on the left side, just like here, right? But in Vancouver, we drive on the right side. The CTO of that company was at UBC giving a presentation, and I asked him if he can use his models in UK, in Vancouver, and the answer is no, because in London, those models were trained on the assumption that you're driving on the left side of the road. Now, when you come to Vancouver, you will have to retrain all of those models. But to answer your question, they're designed in such a way that they take only safe actions when there's something that they can interpret or understand. There was a company called Cruise that went into bankruptcy in San Francisco. For a weird reason. They had these self-driving cars that were running in San Francisco. They were training them, and there were two cars, the cruise car and another human-driven car, side by side. And the human-driven car hit a pedestrian, right? And that person fell under the cruise car, and it dragged that person to the curb and stopped. So that became a big issue, and it was a major legal incident, and lots of other things happened. You can search for this story online. You'll find a lot of things about it. So eventually, Cruise, I think it was a company supported by GM, General Motors. They went bankrupt, and I don't know if they restarted. I don't know. I haven't kept up to speed with the latest news. So we were sort of running out of time, almost 1 o'clock. I'll just show you 2 videos. We'll pause. We'll reconvene after lunch, and then I'll continue there. Okay. So this is... okay, so let me just explain. This is a video that I took while sitting in a Waymo car. And you will see that the car doesn't have a driver. It's just driving by itself. There was some music playing in the car, so you get to listen to that as well. All right, so that's a short video, right? You see these cars. And AI is not without trouble. I thought I would show you this video. This is a parking lot where a lot of Waymo cars are stored or parked in San Francisco. And apparently, they go to work at 4 a.m. in the morning. You can, just like, do you have Uber here? I think you have Ola and Uber maybe. So if you want to call a cab, you can just enter your destination and call the Uber or Ola cab, right? Waymo also works in a very similar fashion. They have an app. You enter your destination, and then you wait. These cars are running around the city. They come to you, and you get in the car. They take you to your destination. So this parking lot had all these Waymo cars. They go to work early in the morning at 4 a.m. They're trying to leave the parking lot at the same time. There's a traffic jam, and they're honking at each other. And the people in the neighborhood apparently complain to the city that these Waymo cars are waking them up early in the morning. So let me show you this video. Let's see if I can play that. Oops. Oops. So, oops, sorry, I trying to use full screen. So they're all trying to get out of the parking lot at the same time.
Thanks for watching. If you like this video, check out.
All right. Sorry? Yeah. Right. Yeah, I don't have what they're trying to do. If all cars are self-driving, then there must be some way of coordinating, right? Or prioritizing who goes first and so on. So I'm sure they're trying to figure out how to solve the problem, or have already figured out the problem. Sorry? Right, yeah. I don't know if Waymo does that, but I will be surprised if they can't communicate with each other. There should be some way of communicating. Right, yeah. They're probably doing that also. Seems like. Yeah, so we're going to pause here. And you have, I think, about, we're going to reconvene at 2:15 p.m.
If somebody has a laptop, you please bring it.
Yeah, so I have a few more slides here, so we may not be able to do Python today, but if you have laptops, please bring them with you. Okay. All right.
So you please come. I will also come to the hostel. Sandeep knows.
So when is Jairam coming? All right. Are we here till 28th, 27th? So do you have, are we doing something on 28th as well? 28th. What is my flight? I think it's on 27th. 28th. I'm just trying to figure out.